Hello again, Physics 243. In this unit, we'll talk about interference and beats. So interference refers to the overlap of waves. So two overlapping waves interfere with each other. So here are two speakers, and they're putting out sound waves. So what's depicted here are the peaks of the pressure variation, let's say. Right? So out here, this is, let's say, high pressure, and in between is low pressure, high pressure, low pressure, high pressure, low pressure, right? In other words, the molecules are bunched together here, spread apart here, bunched together here, spread apart here, bunched together here, etc. And the same for the dark blue, except that's the sound coming from speaker B here. Notice, by the way, that they're synchronized so that this wave comes out at the same time as this wave, etc. Okay, so as these sound waves go out into space, they overlap. And so they interfere with one another. So before analyzing this situation, let's talk about interference and the principle of superposition. So the principle of superposition says that when two waves arrive at the same point in space, you just add them together. So for example, suppose you have this wave and this wave arriving at the same point in space. In this case, let's say that this depicts, again, a sound wave. So this is high pressure, low pressure, high pressure, low pressure, or you can think of it as molecules bunched together, molecules spread apart, molecules bunched together, etc. So suppose that two sound waves arrive at the same point in space and that they're synchronized this way. So that this peak lines up with this peak, that trough lines up with that trough, etc. Well, if they're lined up like that, you get constructive interference because you just add these together. They arrive at the same point in space, and so you get a wave that looks like this. It's got a larger amplitude than just one of them, you see. In fact, it's twice as much here and twice as much on the other direction there. Okay, but what happens if one of these waves is shifted in time relative to the other? So again, here we have two waves, let's say they're sound waves that arrive at the same point in space. So here's one, but the other one is shifted, you see, in time, so that this peak aligns with this trough, and this trough aligns with this peak, etc. Well, when they arrive at the same point in space, they destructively interfere. So they knock each other out because you're just adding these together. See, so here you have something positive, here you have the same amount that's negative, and you add them together, you get nothing. And that's the same all the way through. So that's called destructive interference. Now, in between, you get something else, right? If this lower wave is not shifted, an entire half wavelength, then you get something in between, right? So for example, this peak is not quite aligned with that one. So you get some degree of constructive interference, but the result is not as big as this one is when they're aligned perfectly. So this is somewhere in between perfect constructive interference and perfect destructive interference. Okay, back to the two speakers like this. Let's see what happens at point C. So if we just isolate point C, this is a little bit confusing because now the wave is kind of depicting, is sort of sideways now, right? So this shows the wave fronts because we're looking at the waves from, say, above. And here we're looking at a graph of the pressure versus time that way, or versus space that way. Okay, but anyway, the waves coming from A and B have arrived at C, and notice that they are arriving in step with each other, right? And in particular, this distance is the same as that distance, and since they're synchronized, then they arrive here at the same time. And so we get constructive interference at C. You can see that here too, because the two peaks, the dark blue and the light blue, arrive at the same time at C. Now let's consider D. What happens at point D? So D is shifted up a little bit. You can see that D is straight in front of A, but it's at an angle relative to B. And so the wave goes like this, and when it arrives at D, it's at a minimum. Whereas this wave, when it goes this path and arrives at D, it's at a maximum. So at point D, we have destructive interference. That's because the waves travel different distances. Notice that here we have the peak of the dark blue wave coming from speaker B, and we're in the trough of the wave coming from A. That's the space in between the light blue lines. So constructive interference at C and destructive interference at D. And you can see that in space, the whole pattern fills out. Right? We have constructive here, constructive here, constructive here, constructive here, etc. And here there's destructive interference, destructive interference, destructive interference, etc. Now, this was brought home to me once when I was studying in college. I used to go to a library that had very big ceilings, and there were light fixtures up there that buzzed. And I noticed that as you walk around the room, you would hear the buzzing, and then you'd keep walking a little bit, and then you wouldn't hear the buzzing. And then you'd hear it again, and then you wouldn't hear it again. So this kind of wave interference was happening with that buzzing sound. So for example, I would be standing here, and this is a point of constructive interference because the two peaks, right? I would hear the buzzing here. But then I walk over to this space, this point in space, and I don't hear the buzzing because this is a point of destructive interference, right? It's the peak of the dark blue wave, but the trough of the light blue wave. And then I keep walking and I end up here and I hear the buzzing again. And then I walk over here and I don't hear the buzzing again. And then I walk over here and I hear it again. So that generally is true when waves interfere. And so in order to be able to study and not go insane, I had to find exactly the right spot to sit so that I didn't hear this buzzing. Okay, there's another phenomenon that happens, and that is beats. So the way the book says it is waves can interfere in time. So maybe that's a little confusing. What's happening here is that two waves are arriving at the same point in space, but the waves have different frequencies. And so imagine that you have one microphone, and these two waves of different frequencies arrive at the same microphone. When one of the sources plays by itself, let's say a 60 hertz sound, and you get this blue wave recorded by the microphone. When you turn that one off and you turn on a different source at 50 hertz, this is what is recorded by the microphone, the red one. Now, if you're playing at the same time, then they both arrive at the microphone at the same time, together. And so what happens as you add these things together? Notice that this is a graph of the amplitude versus time, or the displacement here versus time. Well, at this time, the waves are aligned, and so you get constructive interference. But then they shift relative to each other, you see, because there's a difference in frequency. And so that constructive interference decreases until you get to here, where there's perfect destructive interference, because this peak of this blue one aligns with the trough of the red one. So you get no signal there. You don't hear anything. And then as time proceeds, remember this is time, not space, the waves shift again until you get to here, and here you have perfect constructive interference because the waves are perfectly aligned at that point in time. Okay, so what happens is that you hear this sound, and notice that it has a big amplitude and then a low amplitude and a big amplitude. And so what you hear is wah, 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 wah. Right? Loud, soft, loud, soft, loud, soft at a particular frequency. In this example, the beat period is 10 seconds. The beat frequency is 10 hertz. So in particular, the beat frequency is the difference in the frequency between the two waves. So here we have a 50 hertz and a 60 hertz wave mixed together. The beat frequency is then 10 hertz because that's the difference between 60 and 50. So that's what happens. Let me show you some videos of demonstrations that I found on YouTube. I would do this in class, in person, live, but we can't do that. So I have these videos to show you. Let me find them here. Okay, so this guy has a couple of tuning forks. Let's make sure that you can hear this. Hold on. There we go. Okay, I'm starting somewhat in the middle, so you can hear this is the explanation of things when you go to it later.
These two tuning forks are not in agreement. This one has a little extra mass so that it lowers the frequency slightly. Now, if I sound them together, you'll hear them interfering. You can see the effect on an oscilloscope.
Did you hear that? Wow, 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 wow. Those are the beats. This, by the way, is very important in tuning instruments. Like a guitar, for example, you can tune one string to another by listening for these beats. Like you fret one string, a thicker string, you fret it higher up, and you play it simultaneously with a lower, with a higher string. Excuse me, and you want them to sound the same. This is one way to tune a guitar, and so you tune until you don't hear any beats. Piano tuners do this too, except that the notes on a piano, they do create certain beats when it's properly tuned. Here's another example of guys playing trumpet. Do you see what this guy is doing? He's got this slide here, so he's changing the tuning of this trumpet, and this guy's not doing that. So let's take that back again. Where was it? About here. Notice that he moves his hand, and he doesn't. Okay, so when they were out of tune, you heard, some pretty fast beats. And then when he managed to get them in tune, then you didn't hear the beats anymore. All right, so that's the phenomenon of beats. And let's go back to the PowerPoint. I think that's it. That's not it, because I have it. Is this? All right. Okay, here we go. There we go. Okay, so that's the phenomenon of beats. And the thing to remember about beats is that the beat frequency, the frequency of wah, 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 is the difference in frequency between the two waves that arrive at the same point in space. So, quick problem to illustrate this. Two piano strings are supposed to be vibrating at 220 hertz. But a piano tuner hears 3 beats every 3.5 seconds when they're played together. If one of them is known to be vibrating at 220 hertz, what must be the frequency of the other? And another question, is there only one answer? Okay, so it tells you that the beat frequency is 3 beats every 3.5 seconds. Because that's what is here. So the beat frequency is 3 beats divided by 3.5 seconds, right? 3 things happen, and they divide by the time. So that gives you 0.85714 hertz. That's the frequency of the beats. So the other string must vibrate at, we know that the other string is vibrating at 220 hertz, that one of them is. The other string that's not vibrating at 220 hertz must be vibrating at either plus or minus, 220 plus or minus that beat frequency, because the beat frequency is the difference between the two. So the other string has either this frequency or that frequency. And just by listening to the beats, we don't know which one it is. All right, we just need the difference between 220 hertz and the other string to be this. Okay, that's it for this one. Next up, we'll discuss the Doppler effect.